Hello, everyone. Hopefully you guys can hear me clearly. It's not too loud or too quiet. It's 3:05, so I'm going to get started. Thanks for spending some time listening in on my talk titled Strategies for Rate Limiting Network Packet Ingress. So my name is Daolin Qiu. I'm an embedded systems applications engineer at Texas Instruments. My colleague is also a embedded sys apps engineer and also member group technical staff at TI. Unfortunately, he couldn't make it in person with us today, so I will be presenting on behalf of both of us. So before I start with the main content of my presentation, I just had an overarching question to ask the folks here. That question is basically, what do these following applications have in common besides the concept of having to use network connectivity? Specifically, what I'm looking for an answer to is what are these applications at risk of or susceptible to being interfered with? And the answer to that question is something usually along the lines of network storms or network broadcast storms. And for those of you who aren't familiar, network storms are basically events that happen when there is a high network traffic running in a given network of connected devices that causes a high network congestion. And this can cause pretty destructive behavior on especially devices that are on the receiving end of such a high network traffic. And it's commonly caused by a lot of broadcast and multicast traffic that's meant to send to multiple end devices rather than just a single destination device. So how it can happen, in addition to being commonly caused by broadcast or multicast traffic, can also relate to the network topology itself, such as having inadvertently connected a network loop that causes traffic to endlessly loop within itself. So I mentioned when a network storm happens, it could cause pretty destructive behavior, and that's usually causing some sort of high load on the CPU cores of the destination devices, causing those devices to potentially become unresponsive or even crashing. There are several different ways to prevent such an event problem from happening. One solution is to use storm control to limit the broadcast and multicast traffic. There are other solutions like using special protocols like spanning tree protocol to prevent loops in a network, as well as splitting the broadcast domain into multiple subdomains using VLANs. But for the purpose of this presentation, I'm going to be focusing on the concept of storm control to prevent network storms from happening. So what I mean by storm control is specifically the idea of intentionally dropping incoming packets when the monitored incoming traffic rate had exceeded some pre-configured threshold. And in order to do this sort of ingress rate limiting, there are three basic or fundamental methods that I'm going to be looking at examining as a way to do ingress rate limiting. And those three methods are using the TC utility tool, using eBPF, or extended Berkeley packet filtering, and the concept of adjusting Ethernet PHY link speed. I also have in number 4 a bunch of dots to indicate that these three methods aren't in an exhaustive list of all the different ways that you can do ingress rate limiting. And in addition to examining these three methods, I also want to do a comparison of these three methods according to 3 criteria. And those 3 criteria include performance, specifically how well will the CPU load improve with rate limiting with these 3 techniques, how configurable is that rate limit threshold, easy to configure, and then how easy is it to set up and get started using these methods for rate limiting. So this is a brief agenda. I already explained the background and introduction. Next, I'm going to get more in-depth into the 3 different methods that I just described, specifically what they are, how we set them up, and what sort of performance data that we got on those 3 methods. And then I'll end off with a comparison of those 3 methods according to the 3 criteria I described in the previous slide, and end off with some key takeaways. So to start off with the TC utility tool, as a brief introduction, for those of you who don't know, TC stands for traffic control, and it's essentially a Linux command line tool used to configure the Linux kernel's packet scheduler. And specifically, we want to look at leveraging its ability to drop network traffic to be able to do that rate limiting on Ingress that I described. So in our specific setup, we decided to use the TC configuration described here with these 2 TC commands. The first command basically installs a queuing discipline on the Ingress path on the ETH0 interface of our device under test. And the second command will add a filter on that incoming traffic to actually do dropping based on the rate limit threshold that we set. In this specific example, we're setting a rate threshold of about 10 megabits per second. And if the incoming traffic rate is above this, then we start dropping packets until the rate has reached 10 megabits per second or less. So in our specific test environment, we wanted to keep things simple. And so we have here a simple 2-device setup that's directly connected with each other, and sending one directional traffic from a desktop PC running Ubuntu Linux set up as a TCP client, sending traffic to our device under test, which in our case is an EVM featuring 2 A53 cores. Specifically is the TI's AM6442 processor. And our device under test is running as a TCP server. This traffic is going to be unicast traffic for simplicity. It's got no bursting, and as I mentioned, we have set the threshold to be 10 megabits per second, and iPerf TCP is used to simulate a high network bandwidth case. So I wanted to show a GIF of our TC configuration in action performing rate limiting. But for timing's sake, I took a snapshot of the particular section of the GIF that I wanted to demonstrate. Basically, what I have here is that I first start an iPerf stream for 10 seconds without any rate limiting configured to establish a baseline of what the throughput looks like. And for this specific test case, the throughput is looking like about a little over 900 megabits per second. Afterwards, in yellow, I set up the TC configuration as I described the 2 commands in the previous 2 slides. And afterwards, I run the same 10-second iPerf stream and notice that the throughput has now dropped down to less than 10 megabits per second. One thing to notice is that before I set up the rate limiting configuration, there were 0 retries reported by the iPerf output, and this makes sense because every TCP packet is actually getting received by the server, so the server is able to send back an acknowledgement to the client. However, after setting up rate limiting configuration, we do see non-zero retries, which makes sense in this particular case because we are purposely dropping incoming packets on the server side to be able to drop down to that lower rate. And thus, there would be packets that the server would not see and would not know to send back acknowledgement to the TCP client. So I wanted to show a graph over a time interval of around 30 seconds to kind of show further proof that we are able to achieve 10 megabits per second or lower rate limit. Right here, what I have in the y-axis is bits per second. And the blue signal, or blue line here, represents what we see from Wireshark on the TCP client side in terms of throughput. The orange line represents the TCP error rate that Wireshark is able to see, synonymous to the retries that we saw with the GIF snapshot that I showed in the previous slide. And then in gray, I have basically graphed the difference between the blue and the orange line to show what we are calling the Wireshark effective bit rate, basically to take an account for those retries that we showed earlier. And in yellow, I show the average server bit rate, so the bit rate we see from the iPerf server side, averaged out over the 30 seconds interval here. And the key point to take away from this is that the gray line and the yellow line both demonstrate roughly that the throughput has dropped to 10 megabits per second or less. In terms of performance, I also graphed what the average CPU load across the two 853 cores look like when rate limit is not set up versus when it is set up. When it's not set up and we're sending the max throughput of a little over 900 megabits per second, we see a load of about 95% average across the two cores. But when rate limit is set up, we see a drop down to about 4% load. The key takeaway here is that simply by using TC with those two commands, we are able to drop the CPU load down significantly from 95% to 4%. So when we looked at further where TC is actually enforcing its rate limiting, it's actually not accounting for any hardware feature. It's actually being implemented in the middle area of the network stack layers. And here with the black boxes, we're trying to represent some of the key network stack layers with the arrow representing the path that an incoming packet would take. And the point I'm trying to make here is despite TC not actually being enforced in the lower hardware layers, closer to the hardware layers, we still see a significant drop in CPU load. However, that also brings into question if the Mac hardware supports rate limiting and the driver for that Mac is implemented to expose that, then the TC rate limiting can also be offloaded to the hardware, which could potentially result in even better CPU load performance. So in summary, the key advantages for TC utility is it's in its ability to, for that second command that we saw earlier, be able to change that throughput threshold. In our case, we set it to 10 megabits per second, but it could be changed to whatever the user requires. As I mentioned earlier, there is a significant reduction in CPU load from what we saw of the 95% down to about 4% load. And then TC is usually a tool that's pretty usually available in Linux, so there's not really much to do in terms of compilation to set up the tool to be able to use it, as long as your Linux distribution or configuration has TC already available. Some disadvantages include kind of figuring out what those options for TC to use are. Like we saw with the second command, there were a lot of options that I kind of like just skimmed over. Figuring out the specific options to use was, in my experience, a little bit hard to figure out if you're new to the tool. And additionally, this is something I haven't mentioned, but you might have noticed with the GIF snapshot I showed earlier, I had started the iPerf stream to show baseline, had it waited for it to stop, then set up TC configuration, and then restarted the iPerf stream. If I had kept the iPerf stream running while setting TC configuration, the throughput wouldn't actually get updated unless I had restarted iPerf. So this could be problematic, especially in cases where you may not be able to control the source of the high network traffic. So next, I'm going to get into the second method, which is the eBPF method. So I know earlier, the previous presentation in the auditorium did a really good overview and detailed explanation of eBPF, but for the sake of my presentation here, I'm also just going to give a quick rundown. So like we saw, eBPF stands for Extended Berkeley Packet Filter. And basically, it allows a way to extend functionality to the Linux kernel without actually having to modify the kernel source code. So it's basically a piece of code or logic that can run in a safe or sandbox environment in the kernel space. And it gets invoked by system events, such as, for example, an incoming packet. And then in here, I tried to show kind of like an overview of what it takes to compile an eBPF program and then load it into kernel space. And then I know the previous presentation also went a little bit in depth into XDP. For my presentation, I just wanted to highlight that I will be using XDP to demonstrate eBPF as a way to do rate limiting. What XDP is, it stands for Express Data Path. It's basically a packet processing framework that enables early access to the packets at the hardware driver level. So before the kernel network stack can even see the packet, we can evoke an eBPF program using XDP hooks to be able to monitor the incoming traffic and determine some action based on the traffic that we see. In our case, we want to see if the traffic has exceeded 10 megabits per second. If it has exceeded, pass an action back to the driver to drop that packet. So here I tried to show a simplified view of the logic that I'm using for my eBPF program. But I'm not going to go too much in detail here. Just know that the program gets invoked when an incoming packet is received. And what the program is doing is checking during a time window of 1 second if the accumulated number of bits for each packet that came in has exceeded 10 megabits. If it hasn't exceeded, then allow the packet to pass. If it has exceeded, then send an action to drop that packet. I do want to point out that the original logic for this was not written by me. I simply took a fork of another network developer's work and adapted it to run on AM6442 EVM. Project details are linked below. So in our specific test case, we decided to compile the eBPF program on our desktop PC simply because all the packages needed to compile the eBPF program were easily obtainable with a PC that has direct internet connectivity. And then, of course, to load the program, we want to load that onto our device under test, which is our AM6442 EVM. And to be able to actually load the program properly, we also need to ensure that the kernel configuration for that target platform have certain BPF configurations. I've listed the ones that I found were necessary here. And then an optional is to use some tracing configurations to do some BPF debugging. Additionally, I chose to use the IP utility tool to run the command to actually load the eBPF program. So again, I try to show what the GIF, eBPF, Ingress rate limiting in action here, but for timing purposes, I took a snapshot to show what I really wanted to demonstrate. What I have here is basically a throughput or representation of the throughput of iPerf TCP running before eBPF has loaded and to establish a baseline. And in this case, it's a little less than 900 megabits per second. Then when I load the eBPF program, the link of the Ethernet connection gets brought down and back up, during which time the throughput is 0 bits per second, so there is some delay. And afterwards, once the link is back up, we see the throughput has dropped down to less than 10 megabits per second on the TCP server side, which is the target device that we want to look at. And afterwards, I wanted to show that after I unload the eBPF program, I can see that after the link gets brought down and back up again, the original baseline throughput has recovered to about 900 megabits per second. So this is just a quick graphical representation of what I just explained with the GIF snapshot. What I have shown here is that with the high throughput, when eBPF program has not been loaded, we do see the high throughput, and then when eBPF program has been loaded, we see an immediate drop in to a lower throughput of about less than 10 megabits per second. In terms of performance, we see a similar trend where the average CPU load is pretty highly loaded when eBPF has not been loaded. But when the program has been loaded, we see a significant drop to about 1% average across the 2 cores. So one thing to notice here is that the 1% is even less than the 4% load that we saw with the TC configuration before. And this makes sense because the eBPF logic is being invoked at the driver level, which is 2 layers below where TC is enforcing rate limiting. So in terms of advantages, eBPF method, because we're using XDB hook, allows for low latency of being able to process incoming traffic and making a decision on that, simply because XDP allows us to access packets as close as possible to the hardware level. Additionally, we saw very little load on the CPU cores simply by using eBPF, even better of a performance than we saw with TC. And using eBPF allows the user to be able to customize more beyond just setting some throughput rate limit, perhaps even to filter which packets they do want to drop versus the ones that they don't want to drop. So in terms of disadvantages, I'm pretty new to eBPF programs, so for me, there is a little bit of learning curve, a little bit of time that was needed to actually learn how these programs work, how to compile them and set them up. Additionally, in order to take advantage of XDP hooks, to be able to invoke that eBPF program at the driver level, the driver actually has to have support for XDP. If the driver doesn't have support for XDP, it's not that XDP cannot be used, it would just be implemented in a basically a higher level network layer. And then also we saw that there was a requirement of link being brought down and back up, during which there was 0 bits per second. So there's some delay before that rate limit could actually be enforced. So lastly, I wanted to talk about the concept of just adjusting the PHY link speed to do rate limiting. For this, we use the same 2-device setup, except now we're setting the line rate of the Ethernet connection to be, instead of the 1 gigabits per second line rate, we're setting it down to about 10 megabits per second line rate using the ethtool command on the device under test. So we did a graph here where the blue represents the throughput of the iPerf client. The gray represents the throughput of the iPerf server, and then the orange represents TCP errors. One thing to notice right here is that there are no TCP errors, and this makes sense because the way we're doing rate limiting here is not by purposely dropping any packets. We're simply reducing that line rate itself of the physical connection. Of course, this is a very simplified setup, and in the real world, there are likely to be a lot of intermediate devices in the network, such as switches. So for that reason, we also wanted to look at what happens when we insert a switch into the network. And in here, if we had inserted a switch, we see some asymmetric line rate setup going on, where the desktop PC to the switch is about 1 gigabits per second line rate, and the switch to our device under test is, of course, the 10 megabits per second line rate that we set up earlier. With this, we do see some non-zero TCP errors. However, the average server bit rate, throughput rate, and the overall iPerf client throughput rate is still approximately 10 megabits per second or less. I don't have a specific explanation for why we see some non-zero TCP errors, but I think it has to do with the additional switch and asymmetric line rate going on here. Perhaps the switch is doing some sort of configuration where it inadvertently or purposely drops some packets to do that reduction in line rate. So in terms of throughput, in terms of performance, we see that when the link speed has not been brought down, the average CPU load is about 90% average across the 2 cores. But when we bring down the link speed, we see a reduction to about 5% CPU load average across the 2 cores. So still a pretty good reduction in CPU load. In terms of the advantages, with this method, according to certain different network topologies, such as not having a switch or having a switch, we see almost 0 TCP errors. And this makes sense because we're not actually purposely dropping packets to reduce the throughput. We're setting the line rate down to a lower rate. And this method also allows it to be easy and simple to set up. So it's like a quick and dirty way to be able to drop the throughput to recover CPU loading. In terms of disadvantages, using this method really is limited by what the PHY or interface speed or interface mode that we're using. In our specific case, we're using the RGMII mode, which only features the 3 options for link speed, which is 10, 100, and 1,000 megabits per second. So if a user wants some intermediate rate limit, this method may not be the best use. Additionally, we noticed that when we set up the lowering of the line rate with the ethtool command, we do see that the link gets brought down and back up. So during that time, there is some delay before the rate limit gets enforced. So in terms of final comparisons, I mentioned in one of my earlier slides, I wanted to compare Grant's 3 criteria. Those 3 criteria are the performance in terms of CPU load, how configurable are the methods, and how easy are they to set up and use. In terms of performance, I would say eBPF has the best performance out of the 3 methods, simply because we saw the 1% load average across the 2 cores. Additionally, in terms of configurability, eBPF has the highest customizability, full flexibility out of the three, with TC coming in, I would say, in second place because it also has a lot of options to choose from, as we saw with that second command that I showed. And then link speed has the least configurability because it's really limited by the interface mode that we're using. In terms of ease of use, I would say the easiest to set up and use would be the link speed method because we just need to use the ETH tool to set up the limited number of link speeds that we have according to the interface mode. TC is also easy to set up as long as you know what options you want to use for your configuration. And then eBPF has the highest learning curve out of the three, but once you understand how to use it, I'd say it'd be a pretty popular method to be able to do rate limiting simply because it's highly customizable and it's able to achieve really good performance. So what I was trying to take away from comparing against these three criteria is basically where would we use these different methods in different situations to do rate limiting. And from my opinion, I think TC would be useful in a prototyping or experimental application where you would have full control over the source of these high network traffic that's coming in. As I mentioned, it has a flaw that I noticed where the traffic flow has to be restarted before the rate limit can be enforced. So for a deployment environment or a production environment, that may not be a useful tool. And that goes into the eBPF method. I think that would be useful in the production or full deployment application use case because, for example, after you use the TC method to determine what throughput threshold you want to use or what specific packets you want to filter to pass through and which ones you want to drop, then you can go ahead and take those parameters and write them into your own eBPF program to do that logic for you. And of course, with the eBPF method, there is no need to restart the traffic flow, the source of the high network band throughput. And lastly, with the link speed method, I would say this would be useful as a brute force method or a last line of defense as a quick and dirty way to recover the device from becoming unresponsive or crashing as a last resort case. So in terms of takeaways, I would say eBPF using XDP is promising as a comprehensive method to protect against situations like network storms. But that's not to say simple methods like TC or changing the PHY link speed could not be used. It just could be used in different use cases like I had explained in the previous slide. Lastly, one thing you might notice is that all three methods I was examining, none of them actually make use of the Mac hardware to do the rate limiting. All of it was really being done in software. And what I'm trying to show here is that it may not be necessary to use Mac hardware to do rate limiting because we already saw there was a significant reduction in CPU load simply by using each of these three methods. So I want to end off with a little bit about TI, or Texas Instruments, where we have an upstream first mentality and we prioritize being able to upstream fixes and new features up into the open source community, of which we have worked on various projects shown here on this slide. This concludes my presentation. Again, my name is Daolin Qiu. I'm a systems applications engineer at Texas Instruments. My contact and my colleagues' contact details are here. There are some links for more information about the TI products I had mentioned in my presentation here, and the QR code is for more information about TI software. Thank you and for listening, and I'm ready for questions if there are any.